Okay, example 3. Could a hydrogen atom in the ground state absorb a photon with an energy of 5 electron volts? So before we start this question, one of the rules we need to know is that atoms can either absorb the whole photon or none of the photon with no in between. So the atom, for example, cannot absorb 2.5 electron volts of this photon. It has to absorb all 5. Or it can absorb none of that 5. So right now we have an electron, and that electron is in the n equals 1 energy level of the hydrogen atom. I know that because it says in the question that this atom is in the ground state. So the electron that I just drew down here, okay, it has negative 13.6 electron volts of energy. Now let's just say for now that it absorbs the photon. So we're going to add 5 electron volts of energy to this electron. So this is kind of like saying you have negative $13.6 in your bank account, and you get an extra $5 and you deposit it. I want to know how much money is in your bank account now. Now you're going to have negative 8.6 electron volts in your bank account. Now have a look at the energy levels in the diagram. The lowest energy level is negative 13.6, and then the next one is negative 3.4. So negative 8.6 is somewhere here, right? 8.6 is somewhere between 3.4 and 13.6. Now that energy level that I just drew, it's not a real energy level. So in theory, okay, this electron would like to go up to this energy level, but it's not allowed to be there. Because remember in the Bohr model, what Bohr said is that only certain energy levels are allowed. So the electron's allowed to be here in n equals 1, or it's allowed to be here in n equals 2, but it's not allowed to be here in this energy level that I just drew, because that energy level doesn't actually exist in hydrogen. And so because the electron is not allowed to have negative 8.6 electron volts of energy, what we can say here is that the photon is not absorbed. Remember, it's all or nothing. And since this is a not allowed value, it's going to be nothing. The photon's not going to be absorbed. And so the electron will not move up to this energy level that I drew. It will just stay in the ground state. Okay, next we're going to do the same question, but we're going to see what happens if the photon has 10.2 electron volts of energy instead of whatever it said on the last slide. So again, we're starting with an energy of negative 13.6, but now we're giving the photon 10.2 electron volts of energy. And we see that this electron, if it absorbs all of that photon, the electron's going to end up with 3.4 electron volts of energy. So now what we have to do is we have to check if the electron is allowed to have 3.4 electron volts of energy. And the way that I check if it's allowed is I just look at the energy levels that are listed here, and I see if any of them have a value of negative 3.4, and I see one right there that does. So that means that this energy is an allowed value. So what's going to happen is that the electron that's currently in n equals 1 is going to make a transition to n equals 2, and when it does that, it's now going to have an energy of negative 3.4. So now we can say the photon is absorbed, and so the electron makes a transition from n equals 1 to n equals 2. Okay, next we're going to repeat this same process, but with a photon that's 11 electron volts. So again, starting back at the ground state, so negative 13.6, we're adding in 11 electron volts. Let's see what would happen if the electron absorbed all 11 electron volts of energy. we would get, our electron would have negative 2.6 electron volts. Now, negative 2.6, we have to check if it's allowed or not. So just like before, we look at the list and we see, do any of the energy levels have a value of negative 2.6? If it existed, it would be somewhere in here, where I just drew that back line. It doesn't exist though, okay? So again, this is not allowed. So because it's a not allowed value, the atom / electron, same thing, will not absorb the photon because this photon doesn't have the perfect amount of energy required to move the electron up to a higher energy level. So this is actually the same as part A, where the photon is not absorbed. Okay, now we're going to do part D, and part D actually works a little bit differently than parts A, B, and C, and you'll see why in a second. Okay, if we have a electron in the ground state of hydrogen, that electron currently has negative 13.6 electron volts of energy. Remember, what that means is you need 13.6 electron volts of energy to ionize this electron here. So if we give the electron 14 electron volts of energy, that's actually more than enough energy to completely ionize the electron, which ionizing means that we're going to be removing the electron from the hydrogen atom. So watch what happens if I add in 14 electron volts of energy. Then I'm left with 0.4 electron volts of energy. So what will happen is this electron that's in the ground state is going to go up until it's actually out of the atom. Okay, so it's not going up to the 5th energy level, it's going up even beyond the ionization level. So let's say the ionization level is right here. So ionization is where n equals infinity. This electron has more than enough energy to go past the n equals infinity level. So now the rule changes a little bit because when electrons are ionized, they become free. So this electron becomes a free electron, which just means it's not part of the atom anymore. And free electrons can have however much energy they want. So when the electron was part of the hydrogen atom, it could only have these energies that I'm underlining, these allowed values. But when the electron becomes free, there's no allowed values anymore. It can have whatever energy it needs. So what's going to happen is the electron will absorb the photon. So it absorbs the photon and is actually going to have some energy left over. So of the 14 electron volts here, okay, of the 14 electron volts, 13.6 are used to free the electron or to ionize it. Okay, and the 0.4 electron volts that are left over becomes electron kinetic energy. So the electron will leave the hydrogen atom and it will move off into space with 0.4 electron volts of kinetic energy. So what I wanted you to get out of this example is that if the photon energy is less than what's needed to ionize the electron, so if the photon energy is less than the amount required for ionization, the photon will only be absorbed Okay, only be absorbed if this will move the electron to an allowed energy level. Okay, but then, as in part D, if the photon has equal to, we'll say, or more than enough energy to ionize the atom, the photon gets absorbed any extra energy becomes electron kinetic energy.